This is Daryl with Hands-On Cisco Training, episode 16. Today we're going to talk about OSPF areas. It's Friday the 13th, July 2007, and my feed is still at switchpod.com, although keep your eyes open, I might be changing that within the next month or so. So just in case you get disconnected, you can always go back to my website, and again, my email address is ciscotraining@mac.com. We're going to talk about multiple OSPF areas today. Last time we talked about we did an introduction to OSPF where everything was in one area. I talked briefly about how OSPF can achieve more scalability by having multiple areas. The problem is that the shortest path first algorithm is complex. And so if you are a large company with 500 or 1,000 routers or more, and you have them all in one area, your OSPF area is not going to be able to not going to be able to execute all of the shortest path first calculations to converge your network, and your network will fall apart. And that's bad. So let's talk about areas. The map we're going to use today is the same one as last time. I've turned off the switch in the middle. My IP addressing is the same as last time. In fact, I even left the Ethernet interfaces configured, but the interfaces are in the up-down state right now because the switch in the middle is down, or turned off, so I don't have link. I'm going to have three areas. I'm going to have area 0, which is known as the backbone area, is going to be the interfaces in black. So that's going to be two loopback interfaces and then the serial link. And then I'm going to have area 1 is going to be the ones in purple, which is this loopback interface and this serial link. And area 1, another numbering convention that people sometimes use for areas is based on the IP address. An area is a 32-bit number. Well, guess what? An IP address is a 32-bit number, and sometimes it makes sense in sort of a self-documenting way to base the area of an IP address block that you assign to the area. So I've created area 172.16.6.0, which includes this link, which is 172.16.6.1/24 and 6.2/24. So this sort of, sometimes it helps to, and that way you're sort of telling your people, hey, only put IP addresses that are inside this block in that area, and that way you achieve proper summarization. Okay, so let's go through our configuration. The IP addresses are already configured, and we're on the top router first. So let me try this. This way we can sort of see the top router and the config at the same time. So conft, I'll show IP and brief. You can see here are my 4 IP addresses. The Ethernet 0 interface, like I said, its status is up, down, so it's all configured and running, but the physical interface is down because the switch is down. Loopback 0 is 172.16.1.1, serial 0 is 172.16.2.1, serial 1 is 172.16.6.1. So conft, router OSPF, process ID doesn't matter, 7, and then since when you're configuring when you're configuring all the interfaces in a router in a single area, that's when I advocate doing the network 00, 00, 255, 255, 255, 255 area, whatever, because that's simple and it's least prone to errors. In this case, we have multiple interfaces in different areas, so my recommendation is to do something like this. Network 172.16.1.1, 0.0.0.0, area 0. Network 172.16.2.1, 0.0.0.0, area 0. Network 172.16.6.1, 0.0.0.0, area 0. And that's it for that. And let's go to the middle router. sorry, switch my console cable. Conf-T, router OSPF 3. Again, it's a process ID, so it's local on the router. Now, I'm using different process IDs on these different routers just to show you that I can. Again, for consistency's sake, I suggest you pick one and stick with it. And that way all your routers will be configured as near to identical as possible, which again decreases errors. Consistency breeds consistency, and inconsistency breeds inconsistency and errors. Okay. Router OSPF 3, network 172.16.2.2, 0.0.0.0, area 0, network 172.16.3.1, 0.0.0.0. Again, the 0.0.0.0 are don't care bits, area 0, and network 172.16.4.1, 0.0.0.0, area 1. Did I configure that rolling upstairs? Ooh, I configured the top area wrong. I put that 172.16.6.1 in area 0, and I meant to put it in 172.16.6.0. And here I am talking about errors. Something else very important, I don't always do this in these training sessions because sometimes it's, well, in any event, you should always write mem. Nothing more horrible than configuring your routers and forgetting to do a write mem, and then 3 months later you take a power outage, it reboots, it comes up with an old config, and your network is down hard, and you have no idea why, and you don't know what your old config was. Okay, going up to the top router, and I made an error. So conf-t router OSPF 7. Oops, no. There's another error. No router OSPF 78. Router OSPF 7. No network 172.16.1.6.1 0.0.0.0 area 0. Instead, we'll do network 172.16.6.1 0.0.0.0 area 172.16.6.0. And let's go to the bottom router. Router, conf-t router OSPF 1. From now on, I'm just going to use router OSPF 1. I think I made my point that the process ID has no significance outside of the router, and so we're done playing around with that. We're just going to use process ID 1 for the rest of the time. Network 172.16.6.2, 0.0.0.0, area 172.16.6.0, network 172.16.4.2, 0.0.0.0, area 1, network 172.16.5.1, 0.0.0.0, area 1. So in theory, everything's all configured now. Let's see if I did it right. The first thing, let's see how many neighbors I have. I should have 2 OSPF neighbors. Show IP OSPF interface. Ethernet is up, line protocol is down, OSPF is not enabled in the interface, loopback 0 is up, it's in area 1, which is correct. Serial 0 is up, it's in serial 0 is up. It is in area 172.16.6.0, and serial 1 is up, and it is in area 1. Show IP OSPF neighbor. You can see I have 2 neighbors here. I have a neighbor on my serial 0 interface and a neighbor on my serial 1 interface. Let's look at my routing table, show IP route, and now we'll keep it to the size of the screen. Okay, so let's see. I have my connected routes, C means connected, for my loopback interface and my 2 physical interfaces that are on this box. And then here's an interesting one. a new thing. It's an OSPF route. It's an inter-area route. That's what the IA means. 172.16.1.1/32. Now here's 172.16.1.1. It's a /24, but it's a loopback interface. As we discovered last time, loopback interfaces are injected into, or OSPF injects them as host routes, as /32 routes, even though they're not really /32s. And it's administrative distance of 110, because that's the administrative distance of OSPF. It is a cost of 65. The cost of the serial link is 64. The cost of the loopback interface is 1. You add them up to a cost of 65. My next hop is via 172.16.6.1. So to get, if I had a packet destined for this location, then I would send it towards this destination. And if I wanted to get to this destination, how would I do it? Well, to get to 172.16.6.1, I again look at my routing table, and to get to 172.16.6.1, it matches this route advertisement, which is 172.16.6.0/24, which is directly connected. So this is what's called a recursive route lookup. We want to get to this destination. Our routing table says to get to this IP address, you send it to this IP address. And then to get to this IP address, you need to look up in your routing table again. So to get to this IP address, you look it up in the routing table, you see this entry. Oh, that's directly connected out serial 0. I'll spit it out serial 0. In fact, I'll go one better. Show ARP. And I don't see any ARP entries. Oh, the serial 0, it's a serial interface. So we don't need to ARP on a serial interface. ARP is an Ethernet thing. On a serial interface, there's only one host on the opposite side, so you just sort of spit the packet out that interface. Okay, so let's see, it's an inter-area route. Let's look at our OSPF database. Show IP OSPF database. We got a much bigger database this time. So here, OSPF router with ID, this is us. That's our loopback interface, so that is our ID, process ID 1. And for area 1, if you remember, we have two areas. We have area 1 and we have area 172.16.6.0. So for area 1, we have our router link states. There are two routers in area 1, the bottom router and the middle router. The middle router is what's known as an area border router. It has some interfaces in area 0 and some interfaces in area 1. Whereas the bottom router has some interfaces in area 1 and some interfaces in area 172.16.6.0. So for inside area 1, we have two routers, and as you'd expect, we have two router link states. And they're all 80 million too. And then we have the sequence number. And then we have summary network link states. This is something new. Last time we had router link states, and then we had network link states. We don't have any network link states this time because we don't have any Ethernet, but we have something new, the summary network link state. This is a type 3 link state. For area 1, we have 1, 2, 3, 4 summary network link states. And they are all coming from router 172.16.3.1, which is this router. So for area 1, we are getting 4 summary network link states, and the 4 summary network link states are for this loopback 172.16.3.1/24, this serial link, this loopback, and area 172.16.6.0. In fact, here's the one for 172.16.6.0. We'll look at those in a bit in detail. Now, for our other area on our router, we have our router link states. This is area 172.16.6.0. In this area, we have two routers, the top router and the bottom router, and so we would expect two router link states. And we have our two router link states in this area. And we also have our summary network link states. There are 5 of them. And the reason there are 5 is because we get the summary network link states for this loopback, for this subnet, which is the serial link, for this loopback, and then for this subnet, and for this loopback. So this loopback subnet is in area 1, and it goes all the way through the network, through area 0, through area 172.16.6.0, and becomes even though it's directly connected to us, we also learn its database entry, its link state via a summary network link state through all those intervening routers. Okay, let's go ahead and look at our routing table we're in. So we have our 3 directly connected routes, and then we have the 3 routes from our other routers. So 172.16.1.1 is the loopback on the top router, and we learned it from the top router. And 172.16.3.1 is the loopback from the middle router, and we learned it directly from the middle router. And then 172.16.2.0/24 is the serial link on the far side of the triangle, and we are choosing to go towards it via 172.16.6.1, which is the top router. And our cost is the same whether we go with the top router or the middle router. Oh, yeah, and you notice here's the second line. So for this route, we have 2 lines to get there. We can get there at a cost of 128 via the top router, or we can get there at a cost of 128 via the middle router. So we have 2 equal cost paths, and the Cisco router was smart enough to put both equal cost paths into the routing table. Okay, let's go look at our new link state entries. Show IP OSPF database, and then summary, which are type 3. Okay, so in our router, in area 1, we have, here is a summary bit, a summary link state. The link state age is 689 seconds. It is, we'll forget the options. It is a summary network link. The link state ID, which is the summary network number, is 172.16.1.1. This is the host-based route that we get from the loopback on the top router. The advertising router is 172.16.3.1. Now, which is the middle router, and that's sort of weird. This is the loopback for the top router, but we're getting the link state from this router here. And the reason is because we are currently in the summary, currently in link state database for area 1. So we have 2, we're on the bottom router, we have 2 areas, 172.16.6.0 and area 1. But in the link state database right now, we're looking at area 1 first. Now, what's happened is the middle router is an area border router. It knows how to get to this subnet, or rather the /32, because it's always advertised as a host route. What the area border route, and the reason it knows how to get there is because it has the router LSA to get there inside area 0. What area border routers do is what they do not is they do not pass the router LSAs into other areas, because the router LSAs and the network LSAs, you need to execute the shortest path first algorithm and the whole point of having multiple areas is that you don't need to execute the shortest path first. You want to do something simpler, at least in a CPU sense. So what the area border router does is it injects a summary route saying, hey, to get to this subnet, you can get to it through me. And my cost to get to the subnet is, in this case, it'll be 65. So this router, 172.16.3.1, says you can get to 172.16.1.1 with a mask of 32 with a metric of 65. That is all the information there is. And that summary network link state is then flooded, is then injected into area 1 by the middle area border router, and it is flooded throughout the area. But it doesn't change in the area at all. And then if the bottom router needs to calculate the cost to get to this loopback address via the middle router, it calculates that cost because it knows its cost to get to the middle router because it's in area 1. And so it knows its cost to get to the middle router because it has all the information about area 1 in terms of its router LSAs in this case, and network LSAs if you needed them. And it knows the cost of the middle router to the subnet, and then it just adds them. And adding is a lot simpler than executing the shortest path first algorithm. So inside area 1, the bottom router still needs to use the shortest path first algorithm to calculate how far you have to go to get to the middle router. But to calculate how far you have to get to this subnet up here, all you do is add the summary LSA cost to the cost to get to the middle router, which you already calculated. And you end up, in this case, with a cost of 130 via this path. Cost of 64 and 1 for this loopback, a cost of 64. Actually, I'm sorry, it's a cost of 129. It costs 64 to get to the middle router. It costs 65 to get from the middle router to the loopback. And so the total cost is 129. And that is one way to get to the subnet. Now, of course, there's a faster way to get to the subnet through area 172.16.6.0, but which is why we picked a different route. So that is the summary network link LSA. It's got its age. It's a summary network link LSA. The link state ID is the address block that is being advertised. It tells you what area border router to go to get to the address block. It has a sequence number, so that way if the area border router updates it, it will send a new sequence number. It has a checksum, so that way if the LSA is garbled in transit, you can detect that and throw it away. It has a length, which is how many bytes the LSA is in size, so you know when the next LSA starts. It has a network mask, which is how you tell how large the address block is. And it has a metric, which is the distance from the area border router to the destination subnet. It's not telling you how to get to the destination subnet. It just says, hey, if you send the packet to me as an area border router, I can get it to the destination at a cost of 65. Let's look at the next summary link state advertisement. This is the summary network link state advertisement for 172.16.2.0/24. And that is this segment here. Its age was 689 seconds. And the link state ID was 172.16.2.0. The advertising router, this is the area border router that created the summary LSA, is 170.16.3.1, which is the loopback address of the middle router. The sequence number is 80 million ones. This is the first revision of this. We got our checksum. It's 28 bytes long. It's the address block that we're getting to is a /24, and the metric is 64, meaning the cost from the middle area border router to this subnet is 64. Which seems sort of strange because the middle area border router is directly connected to the subnet, but this interface has a cost of 64, which is what is reflected. Okay? let's look at, here's an interesting one. To get to the loopback, which is the link state ID 172.16.3.1/32. This is the loopback on the middle router. You go to the middle router at a cost of 1. And this LSA is not particularly useful because because it's saying to get to 172.16.3.1, you go to advertising router 172.16.3.1, which is sort of loopy. And then here's an interesting one. So the middle router knows how to get to this segment 172.16.6.0 or 172.16.6.1 or 0/24 through the top router. Its cost is 128. 64 for this interface, 64 for this serial interface. And so it's going to advertise it to us. And here's the advertisement. To get to 172.16.6.0/24, you can get there through the middle area border router at a cost of 128. Now, of course, I'm directly connected to that subnet, so I'm not going to go this way, but OSPF still sends that summary information through. Now, here are more summary link states. You may have thought you'd already seen this one. This is the summary link state for 172.16.1.1. Didn't we see that up above? Yes, we did, but we saw it up above for area 1. This is for area 172.16.6.0. The top router is also an area border router. It's connected to area 0 and it's connected to area 172.16.6.0. And so we are going to, so it's also going to generate summary link state advertisements and send them to us through area 172.16.6.0. And here's the first one. It's a it's the address block advertised is 172.16.1.1. It's a /32, and its cost to get there is 1, because it's a loopback address which has a bandwidth well over 100 megabits. Any interface with a bandwidth of 100 megabits or more by default has a cost of 1 in OSPF. So what is my cost to get to that address block? Show IP route 172.16.1.1, and my metric is 65. And the reason my metric is 65 is because I have 2 ways to get there. I can get there by going to the top router via one summary route, or I can get there via the middle router via another summary route. The middle router can get to the loopback at a cost of 65, and I can get to the middle router at a cost of 64. So one choice I have is a cost of 129 to go from the bottom router to the middle router to the top router. Or I can go directly to the top router at a cost of 64, and then the top router can get to the loopback at a cost of 1, which is a total cost of 65. But what's better, a cost of 65 or a cost of 129? I'm going to pick the cost of 65, and that's what the OSPF does as well. Now, what I did was just sort of interesting. I knew the cost from the bottom router to the area border router, and I knew the cost from the area border router to the destination I wanted to get to, and I added them. That's very much like a distance vector protocol. In a distance vector protocol, you add, you know how, you don't know all the information to get to the destination. You don't know the whole path to get to the destination. You just know how to get to an intermediate point, and the intermediate point gets you to the destination. In a link state protocol, you know all the information there is to know about the network. You know that every router is connected to every subnet, and every subnet is connected to every router. You know the full topology information. So OSPF within an area is a link state protocol. Within an area, you have your router LSAs, you have your network LSAs, so you know the full topology of the network. And that gives you optimal routing within an area, but at high CPU cost. Between areas, you just know how to get to the area border router, and then from the via an optimal path using your link state algorithm, and then you just know how far the area border router is from the destination in terms of the cost. And that's sort of distance vector link. So OSPF is a link state algorithm, but these summaries simply get added together, which is not CPU intensive, and that is how multiple areas decrease CPU processing in OSPF. Each area has a smaller topology to execute the shortest path first on, and then the calculations to go to a destination beyond the area is very simple. You just add the cost from the area border router to the destination to your cost to get to the area border router. Okay, let's look at something else. Let's look at the top router for a minute. Show IP route. This one is interesting. I am on the top router, and it says that the best route to get to 172.16.5.1, which is the loopback on the bottom router, is to go through 172.16.2.2. Now let's look at that. I'm on the top router, and it says the best way to get here is through this interface. And my cost to get there is 129, because it thinks that the best way to get there is through this serial interface, which has a cost of 64, to the middle router, through this interface, which has a cost of 64, through this router, and then out the loopback, which has a cost of 1. Now, you and I know that does not make sense. My cost out this serial interface is 64, plus 1 out the loopback. I should be able to get there in a cost of 65, but I can't. Why not? To figure that out, let's look at our database. Show IP OSPF database. Let's look, the optimal path that we should be going through is through area 172.16.6.0, so let's look at our database for that. Here's the database for area 172.16.6.0. I've got the router LSAs, and I've got my summary network LSAs. And in fact, I have a summary network LSA for this subnet. But the advertising router is me. I don't see the bottom router advertising any summary network link states inside area 170.16.6.0. I'm advertising them. Why is that? Well, I'm the top router, and I am on area 0, and I am on area 170.16.6.0. The bottom router is also in multiple areas. It's in area 1, and it's in area 170.16.6.0. So you would think that it would be an area border router, and it would create summary network LSAs, taking the data from area 1 and putting it into area 170.16.6.0. But it doesn't. And why doesn't it? Well, the reason is because OSPF does not have perfect routing information between the areas. The perfect routing information is when you know the whole topology. You know all the routers are connected to all the networks. and all the what networks are connected to what routers and what routers are connected to what networks, and so you're able to calculate the complete topology. Within an area, OSPF knows the complete topology. But between areas, to simplify things, all it knows is the summaries. So OSPF, because it has incomplete routing information between the areas, it is vulnerable to routing loops. So how does it avoid routing loops? The way it avoids routing loops is it says that if you want to communicate between areas, you have to do it through area 0. So area border routers only advertise summary network LSAs when one of the areas is area 0. In fact, another way of saying it is an area border router is a router that borders on area 0 and a different area. So the top router originates summary network LSAs because it's on area 0 and a different area. The middle router generates summary network LSAs because it's on area 0 and area 1, which is a different area. The bottom router does not generate summary network LSAs. It does not allow you to communicate between these areas. If you want to communicate between area 1 and area 172.16.6.0, then you have to do it through area 0. Let's do an experiment. Let's shut down the serial 0 interface and see if we can get to the loopback 0 interface down here. Conf T, int serial 0, shut. And I got some logging messages. My neighbor is down because my interface is down. Now let's look at my routing table. Show IP route. I see my connected routes, but that's it. Nothing else. Why nothing else? Show IP OSPF neighbor. I have a neighbor. I'm still OSPF neighbors between the top router and the bottom router, but the bottom router is not sending me any useful routing information about area 1. And the reason is because it's not supposed to. Only routers that, if you want to talk between areas, you must talk between area 0 and a different area. The bottom, even though, now this interface is gone, I'll move it out of the way. This is what our network looks like right now. We should be able to talk from here to here, but our routing protocol won't let us. And the reason it won't is because it's not designed to. You don't want to segment area 0. When you're building a backbone area, you need to make sure it's fully redundant so that no matter what router or what interface you lose, you avoid segmenting your area. This is a segmented area 0 because this loopback is in area 0 and this loopback is in area 0 and they can't talk to each other. So my network's broken in a big way. T, int serial 0, let's fix network, no shut. Okay, my interface is up, my routing protocol is up, I've got my neighbor, show IP route, I've got 2 inter-area routes, which is what I would expect. You know something? That was fast. I mean, it's like, 10 seconds after I no-shut the interface and the routes are already there, and maybe it would have been there faster. That's one of the cool things about OSPF. Okay. I think that's enough for today.